Hello everyone, I'm very grateful that you're watching this presentation. My name is Lucas Terada. I'm a PG student at the University of Campinas, Unicamp, and I will present the paper called Distributed Energy Management in Residential Energy Communities. To begin this presentation, we brought some motivations. The first one, talk about energy communities. What is this? Energy communities are a local group of residents, business, and public entities that produce, manage, and share energy to boost autonomy, sustainability, and cost reduction. The key of energy communities control is the smart energy management system that coordinates PV, battery storage, flexible loads through monitoring, intelligent control, and optimization to ensure efficiency and balanced operation. And what are expecting with the EMS smart energy system for energy communities? We are expecting lower peaks and lower grid stress, higher self-consumption, and higher renewable energy system share. This is a very important, and a greater resilience aligned with decarbonization goals. What we are proposing in this paper, different from centralizing control, we are proposing a distributed local optimization for each smart home, denoted by SH, within the energy community, denoted by EC. Okay, so each smart home solves its own cost minimization problem tailored to assess its assets like PV, battery and storage system, electric vehicles, and flexible loads, while exchange energy with neighbors. So what's the difference between a distributed and centralized? A centralized system, we have a centralized control that solves all power balance and determining the battery and storage system actions, PV curtailment, and etc. In a distributed local optimization, each smart home has to solve its own cost minimization problem. And what's the advantage? In this case, uh, a distributed local optimization propose uh, less security risk. So why? A centralized system needs all parameters, all data to solve the power balance problem. With distributed local optimization, we're gonna see each smart home has to solve its own problems. So uh, we only need to share the exchange energy between a smart home and another one. So we're gonna see this kind of formulation. So the formulation starts with the objective function, and we have have to minimize the total operation cost for each smart home, including grid imports, P2P trade, and ATMN-based consensus. So let's talk about the constraints. The first constraint is the grid usage. So we have a power balance constraint, a limits of the energy shared or exported. So the energy shared between a smart home and another one has a limit, and unidirectionality constraint of power sharing. So this is a very important constraint because if a smart home starts to export energy for another one, you cannot import energy for this same smart home. So this is why we use binary variables to model this kind of behavior. So the battery energy storage system constraint starts with the state of charge constraint, the total input-output power of the battery, limits of charge discharge in storage system, and just like the battery, the electric vehicle has some constraints like the state of charge of the electric vehicle, just like the battery, limits of charge discharge, and stored energy. In the paper, you can check all these constraints, all the formula equations, and etc. So let's see an example. This example will be the test case. Okay. So in this case, we have three smart homes. So therefore, we're gonna have three severe problems. The first smart home is this that has a PV, a battery and storage system, and uncontrollable loads. The smart home 2 has a PV and electric vehicle and loads, this one. We can check the electric vehicle here. And this smart home 3, we have a PV and battery, like this. Okay, so 3 smart homes, 3 sub-problems. Each sub-problem has its own objective function and constraint, reflecting the unique characteristics of each smart home. So we have 3 sub-problems here. And this setup highlights the framework's flexibility in managing many distributed energy resource configurations and heterogeneous household conditions. So let's see the core of ATMM problem. This flowchart resume the main core of ATMM based distributed optimization. So we start the distributed optimization, and then we have to solve the local subproblem 1, solve local subproblem 2, and solve local subproblem 3. And okay, an important question. Do we have to solve in this order, like subproblem 1, 2, then 3? No. We can solve all subproblems at the same time. For example, like subproblem 1, 2, and 3 in parallel process. Then we have to update dual variables. We have to update the dual variables and check if the convergent criteria is satisfied or not. If the convergence criterion satisfied, we can finish the algorithm and then check the exchange and decision making variables. If not, we have to increase the iteration counter and do the main problem one more time. Okay, so let's see tests and results. Remember this configuration we're gonna use for the test case again. So the model defines the optimal dispatch of distributed energy resource of each smart home in the energy community. So we used the same PV profile for all smart homes. Okay, so the smart home 1 has an 18 kilowatts peak of PV generation, a battery with 20 kilowatts hour with a C rate equal 1. The smart home 2 has a 14 PV generation total generation, a 10 kilowatts electric vehicle charge station, and a 50 kilowatt hour electric vehicle battery. For the smart home 3, it has 20 kilowatts PV generation maximum power generation, 6 kilowatt hour battery with C rate equal 0.5. So we can notice that the battery in the smart home 3 is higher than battery of smart home 1. And the electric vehicle is available to charge between 3 p.m. and midnight. So in this figure, it also have the smart homes load profiles, sorry. So let's see the results. The impact of energy trading costs within the community. So in the paper, we propose 5 test cases. In this presentation, I will show just 2, the case number 2 and the case number 4. The case number 2, the cost of purchase and energy sale are equal, and we determine 6 cents of dollars. And with this test case, we obtain the total net cost for a simulation around $45. And the case number 4, the cost of energy purchase is different from cost energy sell. So we consider 4 cents of dollar for purchase and 6 cents of dollar for selling. And with this configuration, the total net cost is around $44. And okay, we have this kind of total cost, but what else? If we compare with the base case without energy trading, it means uh, each smart home cannot exchange energy to another one. The total net costs around 46, almost $47. So the energy exchange provides economic benefits not only for individual households but also for the community as a whole. And the case number 4 achieved the lowest total community cost with a 44.8% reduction compared to the base case without energy sharing. Just remember, around almost 47 compared with around 44. So to complete the results, we can see an operation of Smart Home 1 PV plus battery energy storage system. So in this case, we can check the usage of battery here, like this. When we have an excess of PV generation, uh, the model prefers export this excess of PV generation to other smart homes, for example. So the operation of smart home number 2. Remember, the smart home number 2 has PV and electric vehicle. Doesn't have a battery. So when we have an excess of PV generation, it's mandatory to export this excess of PV generation to other homes or export to the distribution network. And between 3 p.m. and midnight, it's mandatory to charge the electric vehicle, like this. Okay. Finally, the operation of smart home number 3. Remember, the smart home number 3 has a PV generation and battery energy storage system. And in this case, the battery was used a lot, so we can charge the battery in this between 10 and 3 p.m. Use the battery between 7 p.m. to 9 p.m. because the energy cost is higher between 7 and 9 p.m. And just to confirm, the Smart Home 3 has a bigger battery, offering greater operation flexibility than Smart Home 1. So this is why the battery was much more used. Okay? To conclude this presentation, the first conclusion, the trading prices matter. Well-defined internal prices stimulate exchange, improve local generation use, and reduce grid dependence. A battery is a key enabler. So why? Because it enhances flexibility, load support, and system efficiency through a smart charging charge. And a smart energy community control without a battery is not possible. Finally, overall impact. Coordinated energy sharing with local PV and storage enables lower costs and higher efficiency, contributing to a more sustainable and resilient energy community. So I'm very grateful again for you to watch this presentation. This project was supported by Unicamp, the School of Electrical Engineering Computation, the FAPESP, and CPT.